Sorry. All right, can everyone see in here?
I can see. And
Here? Okay, good. All right, so the dot product. So our learning goals are to find the dot product of two geometric vectors, but more importantly, to find the dot product of two algebraic vectors, which is really cool. And learning to use the dot product to find the angle between two vectors. Yesterday we learned how to add and subtract vectors, and we learned how to multiply a vector by a scalar and then find scalar multiples of those, as well as magnitudes. You guys did a great job of showing your communication using proper vector notation. You knew whether I was asking for a magnitude or the length or a vector. Yesterday's assignment went really well for our first algebraic vectors assignment. So the next step is that can you multiply two vectors together? And if so, how does it work? Okay, and it turns out there's two different ways to multiply two vectors together. And one of those ways, the way we're going to learn today, called the dot product, your answer is a scalar, meaning a number. And the other way that we're going to learn tomorrow, when we multiply the two vectors together, we'll get a vector. Okay. There are two products of vectors and they also have great significance in math as well as physics, and they're called the dot product and the cross product. And today we're going to learn about the dot product. So the definition of the dot product: if u and v are two non-zero vectors arranged tail to tail, like my diagram here, that have an angle theta between them, where theta is between 0 and 180, the dot product, and you say this u dot v, okay, is defined as follows. So u dot v is the magnitude of vector u times the magnitude of vector v times the cosine of the angle between them. Okay, and so since the product, or the dot product, is the product of the magnitudes of the vectors, so we know, for instance, the magnitude of vector u is a number, the magnitude of vector v is also a number, and the cos of an angle is also a number. So to get u dot v geometrically, we're going to multiply three numbers together, which means our answer is going to be a number or a scalar. Okay. Sometimes then, depending on the textbook you use, instead of calling it the dot product, they also call it the scalar product, because your answer is a scalar. So that's the geometric definition of the dot product. So we're going to look at some geometric examples. In our first question, it says, find the dot product of the two vectors defined geometrically in each case. Okay, so we're seeing a picture, we're given the magnitudes of the vectors. So we just need to use our definition of the dot product, or our formula for the dot product. U dot v is going to be the magnitude of vector u times the magnitude of vector v times the cosine of theta. But in our case, the magnitude of vector u is 8. The magnitude of vector v is 5. And the angle between them when they're tail to tail is 71 degrees. And then we can use our calculator in degrees to find that. So I get approximately 13.0. And then in the second diagram, u dot v, again, it's the magnitude of vector u times the magnitude of vector v times the cosine of the angle between them when they're tail to tail. So that's going to be 27 times 12, it's the magnitude of vector v, times the cosine of 90 degrees. And that turns out to be 0, which is one of the most important applications of the dot product, is that if you find the dot product of two vectors and your answer is 0, it means the two vectors are perpendicular to each other, which will have a lot of significance as we go through our vector algebra till the end of the year. So if you find the dot product of two vectors and it turns out to be 0, you can be assured that those vectors are perpendicular to each other. Which, again, it's one of the most significant things about the dot product. And then C. So again, we can find this case, it's going to be A dot B we're finding. So A dot B following the same pattern is going to be the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. The magnitude of vector A is 3. The magnitude of vector B is 2. And the angle is 150 degrees. Which gives us approximately -5.2. Okay, so again, notice that when we had an acute angle between our vectors, our dot product was positive. When we had an obtuse angle between our two vectors, our dot product was negative. And when the angle between our vectors was 90, our dot product was 0. Okay, and that's what I've got written down here. So notice that since the cosine of 90 degrees is 0, the dot product of perpendicular vectors is 0. And that's one of our most super important results here. Since the cosine of an acute angle is positive, vectors forming an acute angle have a positive dot product. And since the cosine of an obtuse angle is negative, vectors forming an obtuse angle have a negative dot product. And also u dot v is equal to v dot u, because in both cases, you're just multiplying the magnitudes of the two vectors and the cosine of the angle between them. All right, so we're going to find some, I guess, useful dot products or things that would be nice to know. So if you dot a vector to itself, you're going to get the magnitude of the vector times itself, but the angle between two vectors that are exactly the same is 0 degrees. Because basically you've got vector u here, and then vector u is right over top of it as well. Those are the same vector. So the angle between them is 0 degrees. And if you want to figure out the cosine of 0 degrees, if you haven't got it memorized, it's 1. So it's magnitude of u times magnitude of u times 1, which gives you the magnitude of vector u squared. So if you dot a vector to itself, you get its magnitude squared. So using that, we can find what I hat dot I hat is. Remember, if we have x, y, and z, I'll just use pens here, I think. I'm just going to take this away for a second. So here's my z-axis, my orange pen. Here's my y-axis, and then my x-axis is coming out at you. You can see that there, hopefully. And we know that I hat is 1 unit in the positive x direction, so 1 unit up the pink pen here. J hat is 1 unit in the green pen direction, and K hat is 1 unit in the orange pen direction. Okay, just a little reminder of what those are. So I hat dot I hat is going to be, according to the dot product, the magnitude of I hat times the magnitude of I hat, and then they're the same vector, so the angle between them when they're tail to tail is 0 degrees. And that's going to be the magnitude of I hat squared, but the magnitude of a unit vector is 1. So it's going to be 1 squared. Don't quite have enough room here. Or just 1. So I hat dot I hat is 1. Write that in different color here, and that's important to know. I hat dot I hat is equal to 1. Similarly, j hat dot j hat is going to equal 1 as well, because it's going to be the magnitude of j hat times the magnitude of j hat times the cos of 0, which is going to be 1 again. Okay, because 1 times 1 times 1. I hat dot j hat on the other hand, so here we've got the magnitude of I hat times the magnitude of j hat times the cosine of 90 degrees. But we know the cosine of 90 degrees is equal to 0. So 1 times 1 times 0 is 0. So this is also an important result. That I hat dot j hat is equal to 0 because they're at 90 degrees to each other. And k hat and I hat are also at 90 degrees to each other. So their dot product would be 0 as well. Because the angle between them is 90. So that's going to be 0 as well. All right, so we can use these results to determine the dot product of two algebraic vectors, which is really cool. It's going to work out to be really nice. I love it. It's one of my favorite things. So we're going to use triple FOIL to do this. So I'm going to start off. You can see that my vectors are defined using multiples of I hat, j hat, and k hat, and that's so that we can use our above results up here, things we know about them. For instance, we know that I hat dot I hat is 1, and we know that I hat dot j hat is 0. So I'm going to start off by saying, you might have to write small here, u dot v is going to be vector u, which is ux, that's just the coefficient of I hat here, plus uy, the coefficient of j hat, plus uz, the coefficient of k hat, dotted with vxi hat plus vy j hat plus vz k hat. So I'm dotting those two vectors together. Notice I'm using the I hat, j hat, k hat form and not the ordered triple form here. So what's going to end up happening is a triple FOIL, triple vector FOIL. So first thing I'm going to do is multiply this first term by each term in the second bracket. And I'm going to dot them. Okay, so I'm multiplying uxi hat, or I'm sorry, I'm dotting uxi hat with vxi hat. So I can just multiply the coefficients out front. So I'm just multiplying these coefficients out front, ux, vx, but then I'm going to dot the vectors, I hat, dot, I hat. Okay, so multiply the coefficients together out front, whatever they happen to be, ux, vx, it could be like a 2 and a 3. And then I'm dotting the vectors, I hat, dot, I hat. So that's the first orange line I've drawn there. Now I'm going to multiply this one by vy, or I'm going to dot that one with vy j hat. So that's going to end up giving me, so I'm going to multiply the coefficients ux, vy, and then I'm going to dot the vectors I hat dotted with j hat. And then the third multiplication here is going to be ux, vz, I hat dotted with k hat. All right, so now I'm going to multiply the second term in the first bracket by each, or dots, I should say, dot multiplication there, by each term in the third. So adding here, I'm going to multiply the coefficients uy times vx, uy times vx, j hat dotted with I hat, plus, so second by second, uy, vy, I hat, sorry, j hat, dot j hat. And then this one by the third one is going to give me UX. Sorry, my bad. UY, VZ, J hat, dot K hat. So there's the pink ones done. And I've run out of room, so I'm going to have to go down here to the next line. So I'm going to put plus here. And now I'm going to multiply my third term by each. So I'm going to multiply by this one, by this one, and by this one. So there's going to be 9 of these when I'm done. So I've got, I'm going to multiply this by this. I'm going to get UZ, VX, K hat, dotted with I hat. This by this is going to give me UZ, VY, K hat, dotted with J hat. And then this times this is going to be UZ, VZ, K hat, dot K hat. So this is the fun part now. So vectors that are perpendicular to each other, when I take their dot product, I get 0. So for instance, I hat dot J hat is 0. Everybody good with that? I hat dot J hat is 0. And 0 times anything is 0. So I can get rid of that term. Similarly, I hat and K hat are perpendicular. They're 90 degrees to each other. So cosine I hat dot K hat is also 0. So those vectors are 90 degrees. J hat and I hat are 90 degrees. So their dot product is 0. J hat dot K hat are at 90 degrees. So their dot product is 0. As with K hat and I hat are 90 degrees to each other. K hat and J hat are 90 degrees to each other. So the only terms I have left are UX, VX, I hat dot I hat, plus UY, VY, J hat dot J hat, plus UZ, VZ, K hat dot K hat. So from 9 multiplications, I went down to 3, but I also know up here, I hat dot I hat is 1. When you dot a vector to itself, you get its magnitude squared, and the magnitude of a unit vector is 1. So I can simplify this further. This is going to be UX VX times 1, which is just UX VX. Same here, plus UY VY times 1, plus UZ VZ. So that's the dot product of 2 algebraic vectors. You just multiply the x components together, and then add to that the product of the y components, and then add to that the product of the z components, and add them together, and you have your dot product, which turns out to be a number. So it turns out to be really nice and easy, and that's just the proof of why that is the dot product of 2 algebraic vectors. Now we'll try it. Okay, so I put it in a box for you up at the top here. If U has components U1, U2, U3, and V has components V1, V2, V3, then then U dot V is U1 times V1 plus U2 times V2 plus U3 times V3. So we're going to find the dot product of each pair of vectors. So we've got U and V here, so U dot V. And remember, watch communication here. So if I want to write out this step first, showing that I'm dotting the vectors, I can. Or you can go straight to the second step here, which is the multiply 10 and add. 10 plus negative 21 is just 10 minus 21. which is negative 11. So u dot v is negative 11. What does that actually tell us about vectors u and v? It just, since their dot product is negative, it tells them that the angle between them is obtuse. A dot b. Again,
Ms. Northwood,
yeah.
I'm wondering, is it better to draw, like, to write in the vectors, like like the pair form for the vectors in, or to write in the numbers multiplying each other?
Okay, so once I'm used to it, John, I always go straight to the second step.
Okay.
Okay, just because the amount of vector algebra you're going to do, you don't want to write that out if you don't have to. If it helps you, write it out, but if not, then go straight to just multiplying, which I'm going to start doing at C. Okay?
Okay.
So again, here I'm going to multiply the x components, 3, plus the y components multiplied together, which turns out to be negative 15, plus the z components. So that's going to give me 0. What is that? What is that? Sorry, go ahead.
After you're done this, would you be able to post a picture of what you just did? Because my screen was like super blurry and I could barely see what was going on.
Okay, so
Yeah, me
Hannah,
too.
after each, when I post each video, I take pictures of the sheets and post that file with the video. So when
Okay.
you see the video pop up, there'll also be like a file that has the lesson with me of like I do it on Cam Scanner, just like you guys do.
Okay.
So it'll be there. Okay, so if you get the dot product being 0, what does that tell you about the vectors? It doesn't ask, but you should note, okay, if you get the dot product to be 0, you know that A is perpendicular, which this is the perpendicular symbol. Those vectors are perpendicular to each other. Okay, so now I'm going to go straight to just multiplying by looking at the vectors here rather than writing out that first step. So I know I'm doing the dot product, so I'm thinking negative 2 times 1 is negative 2. Then I'm adding 2 times 7. So that's positive, so I'm adding 14. And then I'm adding 3 times negative 4, which is negative 12. So that's minus 12. And when I add those 3 together, I get 0 again, which also means u and v would be perpendicular. Okay, so I got u dot v is 0. Notice notation here. So one of the biggest mistakes I see people making is they do this. Do you see how they put commas between them? Don't do that. Remember, this is just a number, and the way you find that number here, our final answer, is you multiply the components and add them. It's not a vector, okay? As soon as you introduce commas there, then you're saying you think it might be a vector, even if you don't include parentheses, okay? So just be careful about that. And then here, Q is given to us not as an ordered triple. So the first thing I would do is rewrite Q as an ordered triple, negative 2, 1, negative 4. And then I'd find V dot Q. So I'm going to multiply 3 times negative 2 is negative 6. Add 0 times 1, which is 0. So I don't even have to show that. And then add negative 1 times negative 4, which is positive 4. So V dot Q ends up being negative 2. Okay, so it actually is really simple to find the dot product of 2 algebraic vectors. Really simple, okay? You just have to practice it a few times, get the notation down and you'll be fine. Okay, so here's one that's involves a little more vector algebra. If vector A is 4, 0, negative 7, vector B is 2, 5, negative 1, and vector C is 4i hat minus j hat plus 3k hat, find vector 2a minus c dotted with vector B. Okay, so first thing I would do is rewrite C as an ordered triple. And then I want to find this here, 2a minus c in brackets. So that's telling me to do that part first. And then I want to dot that result with vector B. So it's kind of combining yesterday and today. So you guys did a great job. So vector 2a is going to be vector 8, 0, negative 14. Okay, so that's vector 2a minus vector C, which is 4, negative 1, 3. Okay, so that's in brackets because I'm finding it first. Vector 2a minus vector C, and I'm going to dot that with vector B. Okay, so I'm going to finish this subtraction of vectors here and get a vector. So when you subtract two vectors, you get a vector. 8 minus 4 is 4. 0 subtract negative 1 is positive 1. Be careful with the signs. Negative 14 minus 3 is negative 17. And now we're going to dot that with vector 2, 5, negative 1. And then we know dot is multiply the components and add. So 4 times 2 is 8. Plus 1 times 5, so plus 5. And then plus negative 17 times negative 1 is positive 17. So that's going to end up giving us 13 and 17, which is 30. So there's our dot product of vector 2a minus c dotted with vector B. Any questions about that one? Kind of mixing up yesterday and today. Okay, good. All right, now we're going to learn one of the most useful applications of the dot product, which is finding the angle between algebraic vectors. So this is also very cool. So use the dot product to find the angle between vectors u and v, given them. And then after that, we'll go over and graph them, and we'll use like SOHCAHTOA to figure out the angle, and we'll compare and make sure that they're the same. So the way we're going to use the dot product to find the angle between two vectors is we're going to go back to its geometric definition, and that is that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. That's how we started the lesson with our geometric definition here. Okay, so if we rearrange this for cos theta, we would divide both sides by the magnitude of u and the magnitude of v, and we'd get that the cos of the angle between the two vectors when they're tail to tail is their dot product divided by the magnitude of each vector. So all I've done is got cos theta by itself. So this formula is a really important one. This is our formula for finding the angle between two vectors. So whenever you need to find the angle between two vectors in 2 space or in 3 space, there's your go-to formula. The cos of theta is equal to u dot v divided by the magnitude of u times the magnitude of v, which are all things we can find if we're given our vectors algebraically. So I'm just going to use this formula for this specific question. So the cosine of angle theta is equal to vector u dotted with v. So I know that to do u dot v, I'm going to do negative 5 times 3, so that's negative 15, plus 2 times 4 is 8 over the magnitude of vector u. So the magnitude of vector u, are you guys good with it's going to be the square root of 5 squared plus 2 squared? So can I just write root 29 here and everybody understands how I got that? Or does anyone have any questions about how to get root 29 for the magnitude of vector u? We're good? Okay, so then I'm going to multiply that by the magnitude of vector v, which is going to be the square root of 25, which I know is 5. But I'm going to leave it as square root of 25 just to make my calculation easier. So negative 15 plus 8 is negative 7. And then if I'm multiplying two radicals together, it's the radical of the product. So I can do 29 times 25 and get square root of 725. And theta is going to be the cosinverse of that. Which is what you want to be able to put in your calculator. So you want your calculator in degrees. And some calculators you're going to do negative 7 divided by the square root of 725 equals, and then press shift cos or second cos. In other calculators, you press shift cos first and open up a bracket, then do this calculation and close your bracket. It depends on your calculator, but make sure you're in degrees. And if you enter that calculation correctly, you should get approximately 105 degrees. And it makes sense to get an obtuse angle because our dot product was negative 7. U dot V ended up being negative, which we know leads us to an obtuse angle between the vectors. Did anyone else get 105?
Yep.
Yep, okay, good. All right, so now what I'm going to do is prove to you that that is actually the answer using our diagram here and just plain old SOHCAHTOA, and then we'll know in our heart that that's true, and then we'll use it in 3 space to find the angle between two vectors there as well. So if I have the vector negative 5, 2, we know that that's the vector that starts at 0, 0 and ends at negative 5, 2. So, oops, there's a little bobble there. So that's vector u. And then vector v starts at 0, 0 and ends at 3, 4. And we want the angle between them when they're tail to tail right here, which is theta. But what I'm going to say we can do is if we find this angle here, because that makes a 90-degree angle, so I'm going to call this angle alpha. And we know that this distance is 5 and this is 2. So we can use tan of alpha is 2/5. So alpha is going to be the tan inverse of 2/5. Which is 22 degrees approximately. And then I'm going to also make a right triangle over here. And I'm going to call this angle beta. So again, I can use tan. Tan of beta is opposite, which is 1, 2, 3, 4 over 3. So beta will be the tan inverse of 4 over 3. which turns out to be 53 degrees approximately. So because of a straight angle, we know that beta, theta, and alpha all add up to 180 because they're parts of a straight line. So I can say that theta is going to end up being 180 minus alpha minus beta, or approximately. So I'm going to do that on my calculator. 180 minus 22 minus 53 is approximately 105 degrees, which is what we got using the formula that involved the dot product. So we know it works, and that is going to be our go-to. So now we're just going to practice using this formula for finding the angle between two vectors when they're tail to tail. So our next question says, find the angle between each pair of vectors. So I would start off saying cos theta is going to be u dot v over the magnitude of vector u times the magnitude of vector v. And then I'm going to do the dot product in the numerator. So I know that's multiply and add. 6 times -1 is -6, plus -5 times 3, which is -15, over the magnitude of vector u. So the magnitude of vector u is going to be the square root of 36 and 25, so the square root of 61. And the magnitude of vector v is going to be the square root of 10. 3 squared plus 1 squared. So the cosine of theta is going to be -21. So I'm expecting an obtuse angle again, over the square root of 610. And then I can put that in my calculator. Theta is going to be the cos inverse of -21 over the square root of 610. Entering in your calculator is one of the hardest parts, I think. I got 148 degrees approximately. Did anyone else get that?
Yes, I think that's a good number.
Okay, good. All right. If you need help with your calculator, stay around after we're done the Google Meet, and I'll see if I can help you on the Meet. Okay, so for B, now we're in 3 space, and we still want to find the angle between those two vectors. So immediately when I look at vector V, I want to restate it as an ordered triple, using that different vector form there. And then I'm going to use my formula for the angle between those two vectors. So cos theta is u dot v over the magnitude of vector u times the magnitude of vector v. So u dot v, multiply and add, so -3 times 5 is -15. Subtract 4, subtract 2. We're going to be getting a obtuse angle again. The magnitude of vector u is going to be the square root of 9 plus 1 plus 4, so the square root of 14, multiplied by the square root of, so it's going to be 25 plus 16 plus 1, 42. So it's going to be -21 over the square root of 588. Theta is going to be the cos inverse of that. So the cos inverse of -21 over the square root of 588 is exactly, I don't need the dot, exactly 150 degrees. Any questions for that one?
Did you set that up so that it would be exactly 150 degrees?
I might have. Okay, our last question. Show that the vectors VAB and U negative BA are perpendicular. So again, the biggest outcome of the dot product is that if the dot product of two vectors is 0, then we know that they're perpendicular. So we would try to find V dot U. I'll actually write them out. V dotted with U here instead of doing it in my head just to enhance the fact that it's true. So if we multiply A times negative B, we get negative AB. And add B times A. B times A is BA or AB as well. And then when you add those, you get 0. So since V dot U equals 0, vector V is perpendicular to vector U. So since V dot U is 0, vector V is perpendicular to vector U. So we've shown that. Okay, so I'm going to stop there. Stop recording.